Now, suppose that we have a spring, and the length of that spring is the small l. Well, but then imagine that you put a certain weight on the spring, right? So here you kind of attach something, an object to the spring. Then what's going to happen is that the spring will be strained, and balancing the forces, so meaning that now if the object is not moving, then of course according to second Newton's according to the first law of motion, all the forces that act on the object are balanced, right? So, and here the force that pulls the object upward is the spring force, so this is from Hooke's law, and the force that pushes the object downward is the gravity, force of gravity. So, and then balancing them, we can find the spring constant, K. All right. So furthermore, so imagine that we are going to pull it a little bit further and then release. So let me show it to you on some example. So suppose that I have an object and then I'm going to attach it to this spring. Okay, so if the whole spring weight system is not moving, it means that while the object it just strained the spring, and then everything is balanced, right? So, but then suppose that we're going to pull it a little bit further and then release. Then of course what we're going to see is that it's going to oscillate around this initial position, around the equilibrium position, so where the forces were balanced. Now we are going to write down the differential equation of the motion. So now suppose that this u of t is the extra displacement, right? So we have the length of the unstrained spring. Then when we attach the object to it, so it strains it a little bit, so that's the additional displacement is called L capital. But then when we pull it a little bit further and release, it's going to start oscillating, and then the magnitude of oscillation at time t is going to be denoted by u of t, right? So then u of t is going to be positive or negative, right? So positive u of t means that it goes down, negative means it goes up, or vice versa. Then writing down Newton's second law of motion, we get this, right? Because the left hand side is the sum of the forces acting on it, and the forces are the force of gravity, right? So that's gravitational force, and this is the spring force from Hooke's law, spring force. Well, but then when we expand it and simplify, we are going to get this equation, this or this. Both equations can be applied to model oscillation of a spring mass system. But then usually, of course, the spring constant K, I mean, how do we know the spring constant K? We cannot really measure it directly. So usually what we do, we can measure G, the gravitational acceleration, and we can measure L, the displacement of the spring. And then if we measure G and L, then we can, of course, and if we know the mass of the object attached to the spring, then we can deduce k. So then we set up the characteristic equation. So the characteristic equation has two purely imaginary roots, so which means that the general solution is going to be a combination of cosine and sine. Now let us go through an example of a word problem on this sort of topics. So here a mass of 1 kg stretches a spring 9.8 centimeters, right? So which means that this is our L capital, and 1 kg is our M small. Suppose that the mass is additionally displaced 5 centimeters and released. So what is this additional displacement? So the displacement by time t is denoted by u of t, and then additionally displaced and released means that at the initial moment we know that u of 0 is 5 centimeters, and then, well, the word released means that so we just let it go. So it means that the initial displacement is 5 centimeters, but the initial speed, the initial velocity is 0, because we did not push it further on purpose. So we just let it go. Alright, so let me go through this. So now a good idea is to convert everything from start to the same units, because otherwise you will it will be a mess and you will get confused. So now we are going to convert everything to meters, because g is measured in meters per second square. So this is all the data that we have in meters rather than in centimeters. So then we have computed the square root of g over L, and then this is the general solution. And now, using the initial condition, we can solve for the constants. So, and then what we see is that one of the constants is just 0, and the other one can be deduced. So the answer is this. Okay. So the general solution of a free undamped system can be written in this form. It is completely fine to write it in this form, but very often it is also written in this form, which is called the R formula. So if you don't remember how to convert from one to another, then I suggest that you either try to do it now to solve this problem, or you can just Google R formula and you will see. So, but this is material from, I think it's from secondary school. It's very simple trigonometry. Well, the reason R formula is convenient is because R formula is kind of naturally related to the initial condition. So if you want to so this is the graph of the general solution of an undamped oscillation. Then if you want, you can play with this graph, so you can change some parameters and see what the graph looks like. So I've prepared this plot for you. So for example, you can change the acceleration due to gravity from 9.8. So imagine that, I don't know, you are going to the moon. So then acceleration of gravitation is going to be 1.6 or 1.7. But then, yeah, you see, if you change acceleration due to gravity, then in the formula you have acceleration due to gravity is in the numerator of at the cosine, and so the bigger it is, the higher is the frequency. The smaller it is, the smaller is the frequency. So smaller means longer period and less frequency. But then if you change the displacement, which means you actually are playing with the mass, because more mass means more displacement. Or you make the spring softer. So if you make the spring softer, then the initial displacement is going to become bigger too. So then you see that it also has a certain effect on the solutions. So I hope it's clear. So now that's the end